Okay, so let's get started with chemical bonds. As I said previously, chemical bonds are results of the relationship between electrons from different atoms that are basically close proximity enough to develop some kind of energy relationship and start reacting. And how they react determines the type of bond they are. And basically, the type of bond they are and how they react determine whether, or the types of elements they are, whether they are metals or not metals, right? And so, like I said before, you're going to have different electrons. It's kind of like if you had somebody, let's do this. Say you have a couple people right here, right? A person right here. And then zombies are going to eat them, right? And so they're going to start coming around. And so you're going to have a group of zombies that are really close, but that's not going to stop zombies from basically coming around, right? And having all these different areas from that center that you can find zombies. And so that's essentially how electrons are. You have protons and neutrons kind of in the middle here. And then you're going to have these different areas coming out from the center that you can find electrons. And the ones that are on the outside, or the farthest from the center, those are what are known as valence electrons. And those are the ones that are going to interact with other atoms. And it makes sense because they're on the outside. For instance, if you have more people over here, these zombies that are here aren't going to be bothered by the people over here. They're eating these guys, right? Which ones are going to end up noticing? These guys here are going to be like, oh, there's something I could have out there. And so they're going to come and interact with this guy. And that's the best way that I can kind of describe how electrons work. That the ones that are closest to the center, they kind of have this gravitational pull that's happening where they're close enough, where these guys on the outside can basically interact with something else because they're farther away. And so the electrons that are towards the outside, they're found in what's known as their valence electrons, found in the valence shell, or the shell towards the outside. Now, when we're bonding, there's a couple rules that we're going to talk about. There's going to be basically electrons, just like people like to be in pairs. So you're going to see that if you have one electron by itself, it's going to be kind of unstable and so its whole purpose, and you can go life in quotes, is to try to be stable and find another electron to pair with. And so that's one of the bonding rules, right? Now, depending on location, the closest to the middle or the nucleus, there's a maximum of 2 electrons that can be there. And then so once they fill those 2, they're happy. But outside that, there's more electrons that can be there. And basically you'll find out there's this thing called the octet rule that says when they're farther out, we want 8 electrons there. That might sound confusing, but by the end of this, you'll completely understand everything. So let's talk about, I keep saying shells and orbitals. So let's talk about the difference between both. And so we're going to focus really quick on this guy right here, neon. So let's try this and see if you can remember. What's the atomic number? If you said 10, you'd be right. What's the atomic mass? 20, right? So the number of protons is what? 10. number of neutrons is 10, and the number of electrons is 10, right? So 10, 10, 10. So hopefully you figured that out. So that is neon. So let's talk about how those electrons are placed around the nucleus in their orbitals. So, like I said, atomic orbitals have to do with these clouds. So if you watch Penguin Prof, she has a great way of saying where the electrons are trying to help you imagine what an electron looks like. Well, it's kind of like if you have cotton candy, right? And you have this big, beautiful thing of cotton candy and ask, where's the sugar? Well, the sugar is everywhere, right? It's part of that cotton candy. It's there. So that's kind of how electrons are. And so when we're talking about the areas or the orbitals, we can find electrons. There are different orbitals, and we're only going to start with the very simplest of orbitals at the beginning. So if you look here, this is what's known as a 1s orbital. It's the smallest. This little purple dot that's in the middle that you can see here, right? If I can get there. That's the nucleus. That's where you're finding the protons and the neutrons. And do you see this area that comes around that? That is the orbital. And you can think S for sphere, and that's the first area you can find electrons. And so on here, there's a maximum number of electrons that you can find in an orbital, and that is 2. And so this 1s orbital has 2 electrons. Hopefully that makes sense. As a maximum. Can you have less than that? Yeah, well, if it has less than 2 electrons, like hydrogen does, it only has 1, right? Well, then only 1 little electron will be there. But I said earlier, electrons like to be in pairs too. So what makes helium want to react with other things? Well, to find another electron to put in his shell. And so that's one of the principles of bonding, trying to become stable, having 2. But that's what we're going to talk about here in a second. Right now, we're just talking about where we can find electrons and the location or the area. So when we're talking about that, when we're talking about the electrons there, we're saying that we can have, in this 1s orbital, you can have a total of 2 electrons max, right? In that area. So they're just kind of in there, negative energy. Now this is the next orbital out, the next bigger one, and this is what's known as a 2s orbital. You can think 2s as in double the size. That's how I remembered it. And in here again, you can have the total of 2 electrons. So this basically, if you look at it, guys, it's just farther out. That's all it is. Okay? Oh. So 1s, 2 electrons, 2s, 2 electrons, right? So, and these are p orbitals. And I say p, don't they look like flower petals, right? So, and they go aligned based on, if you remember in math, you have the, right, x, y, and then coming out from it is the z-axis. So it's in 3 dimensions. So this is the 2px, and it looks like this infinity, so 2 electrons can be there. This is the y, 2 electrons can be there, and this is the z, 2 electrons can be there. So in the full p orbital, it's 2, 4, 6 electrons can be overall. So let's take our neon really quick. Remember, we had 10, 10, and 10, 10 protons, 10 electrons, 10 neutrons, and 10 electrons. Remember? So I'm going to use some purple here. So let's look at what neon looks like, right, when it comes to orbitals. Well, if we have 10 electrons, then this is the closest to the center, so we're going to fill that one first. So how many are the total that can be there? You're going to get 2 electrons here, right? So then you can go -2. You have 8 left over. Well, the next one out from the center is this guy here. And remember, we can have 2 here. So you -2 more, and then you have 6, right? Well, then you're going to have 2 here, 2 here, and 2 here, which 2, 2, and 2 equals 0. So this is the configuration for neon. Now, they're not just hanging out. If you look, they all overlap. Okay? So if you look at the center right here, that area is that 1s orbital here, right? So when we're talking about orbitals, we're talking about basically the locations we can find them. When we're talking about shells, we're talking about how much energy that the electrons that have incorporate, right? And so you can have orbitals, several different orbitals being in the same shell. And so let me show you what I mean by this. So if you look down here really quick, oh no, it's about to go all the way. So if you look here, right, do you see how this guy right here only goes as far? Where these 4 go out here. So when we're talking about shells, we're talking about how far the electrons come out, thus how much energy. The farther you are from the center, the more energy the electron has. You can think of the fact of, and this is just how I remembered it, that the farther out, the more energy it had, the more energy it needed to hold on, right? That's not necessarily, but it helped me remember it. And so on here, this guy is the only one that goes out that far. So the 1s orbital is in the first shell. So that first shell from the center, if this is the nucleus here, right, can have a total of 2 nuclei in it because that's the maximum that shell can hold. Okay? But if you look at these guys here, do you see how this 2s and this p, x, p, y, and pz, they all go out here, right? So because they all go the same distance out from the center, they all have the same amount of energy. So they're in the second shell, which can have a maximum of 8 electrons, because if you see, this one has 2, 2, 2, and 2, added all together is 8. And if you look on, if we went one more farther, there's another 8 rule as well. And this is somewhere over here is where it gets, depending on transition metals, if you get into chemistry, it gets really weird because things like iron don't quite behave this way. But for the sake of this course, this is the farthest we're going to go and the most complex. So in order to fill, for this shell to be completely stable, and or this shell, they need those number of electrons. So if you see in this guy that's right here, his first shell is filled, right? Look, this is the first shell, right? And there's 2. And this is the second shell, and it's 8. So that's why he's stable. He's a Nobel gas, right? He doesn't interact because he's completely stable and he doesn't need anybody else. Let's move on from this and let's look at other things. And let's see what things will form bonds. So here we have hydrogen, and he has number of protons 1, number of neutrons 0, number of electrons 1. So when we consider bonding, we look at the number of electrons. So when we're looking at here, how many? So we have, so protons and neutrons, right? You have 1 and 0. And then when we're looking in that first shell, how many are there? Well, we have 1 in the first shell, right? How many do we need to be stable? We need 1 more. So that's going to make him basically react to find 1 more electron. Let's look at carbon. So carbon has 6 protons, 6 neutrons, 6 electrons. So proton, neutrons. So how many do we have? So we have 6 electrons. How many are going to be in the first shell? 2. So we go minus 2. We have 4 left over. How many are in the next shell? 4. Well, is he stable? No. Why? He needs how many to be stable? We need 4 more to be stable. So he's going to interact with stuff to try to find 4 more electrons to be stable. Let's look at oxygen here. He has 8, 8, and 8. So how many does he have in the first? 2, right? 8 minus 2 equals 6. How many does he have in the second? 6. How many more does he need to be stable? We need 2 more, right? And then let's look at this. And this is kind of showing you, right? So we have 11 electrons here. How many does he have in the first shell? 2. In the second shell? 8. And the third shell, he has 1. How many more does he need to be stable? 7 electrons, right? So that can tell us how many valence electrons. That's the long way, right? Now, just to let you know, there is an easier way to see, besides all of this, to see how many valence electrons you have, is by looking at the periodic table. And these numbers up here tell you how many valence electrons. And they go all the way down, right? So you have 1, 2, 3, 4, 5, 6, 7, and 8. And that's what's important. Some of these down here, these transition metals, get really weird. So we're not going to focus on these because most of what we're concerned with is the nonmetals, right? So that tells you kind of the difference between orbitals and shells. Now, as you can see here, these guys, will they react with anything? They won't, right? Because this has 2 electrons in its valence and this has 8. So these are stable. No reaction. And that's what RXN means. Now, when we're talking about chemical bonds, we're talking about when atoms are unstable, like we have just demonstrated how to figure it out, and how they will bond with each other, right? And the resulting bond will result in what's known as a molecule. And so this is showing you right here, you have water, which means that you have 1 atom of oxygen that's bonding with 2 atoms of hydrogen. This is carbon dioxide, right? 1 molecule of carbon is bonding with 2 molecules of oxygen. And basically, the best way that I can say is how they relate in the real world to how strong they are. And strong is basically when you're talking about biological systems. So if you talk about which one, when you're talking about, these are the three major bond types: ionic bonds, covalent bonds, and hydrogen bonds. And when you're talking about strength in just general, ionic bonds are the strongest, covalent bonds are the second, and hydrogen bonds are the third. But when you're talking about in a biological system, atoms are subjected to water, which changes the strength. In water, covalent bonds are the strongest. So in water, this is the strongest, this is the second, and this is the third. In water, which is in biological systems. So when you're talking about this, you can think of the strength. Covalent is the strongest, so it's equivalent to marriage, right? Ionic is equivalent to if you're dating someone, and hydrogen bond is equivalent to a one-night stand. It's the best way that I can basically talk about it in terms of real world relationship-wise, right? It doesn't last forever, or acquaintances. And so, but this is just in water in a biological system, right? I've already talked about what it's like outside of water. So, we're going to go over and I'm going to show you really quick a video. And then from there, we're going to talk about the three bond types.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
So, let's talk about ionic bonds. So, ionic bond is going to be between two metals, between a metal and a non-metal. And so that's going to cause the atoms, one of them to either lose and the other one to gain, or vice versa, electrons, right? So it's a transfer of the valence shell electrons from one atom to the other. So when the transfer happens, one will become what's considered an anion, a negative charged ion, because it has more electrons now than it had protons, and one to become a cation because it has one more proton than it has electrons. And because they have this negative charge, one's positively charged, one's negative, it's going to allow them to basically attract to each other, and that's what causes the ionic bond. So it's the differences in what's known as electronegativity. And that pull towards itself, that very negative or not very negative, is the positive and negative aspect of these. And so the number of electrons in the outermost orbital of the atom determines how electronegative it is, and it will determine some of this bonding. So let me show you what I mean by all of this. And so here we have sodium. It has 11 electrons. So in the first orbital, it has 2. In the second orbital, it has 8. That makes 10, right? And then the last one, it has 1. So how many does it need to be stable? It needs 7 more. And here's chlorine. And so here you have 2, and here you have 8, right? And then here you have 7. How many more does it need to be stable? Needs 1 more, right? Now, if you look at this, in order for sodium to be stable, it needs 7. How hard is it for you to find 7 friends to go to the movies with? For me, it's darn near impossible. So look at what can happen here. Do you see how it could be easily fixed if these guys are right next to each other, that this moves over here, and now instead of having these outside valence, it looks like this, right? And then this guy adds right here. So how many does sodium now have on its valence shell? 8 electrons. Is it stable? It is stable, right? And now we have 8 in its valence shell here. So it's stable. But let's look at what's happened. So if you look over here, right, the sodium, initially it had 11 protons, right? 12 neutrons, 11 electrons. What happened to its electrons? It got rid of 1, right? It lost 1. So now it's at 10 electrons. Let's look at chloride. It was at 7 protons, 18 neutrons, and 17 electrons. Well, it gained 1, right? So now it's at 18 electrons. Well, let's look at the total number. If we're at 10 electrons here, so we have 11 positive charges, right? And we have 10 negative charges. This guy, initially it was neutral, right? Because it had 11, 11. Now it has 11 and 10. So now this guy is positive because he's lost an electron. This guy, he's gained 1, right? He has 17 protons, which is positive here. But now we have 18 negative. So he has 1 more negative. So he's become negative. So when you have positive or negative atoms, they're called ions. A positive ion is called a cat. And if you look, it has a positive in its name. Or you can say the cat has a positive disposition, which we know that's not the case, right? And then you have an anion, which I think a negative ion, right? And so positive and negative attract. And this allows this to become sodium chloride, which is salt. And so if you look here, it's really easy. Let me get out of this. And go back here. Sodium chloride. You have sodium over here. You have chloride over here. And so you have a metal and a nonmetal, and that's what forms ionic bonds. So true or false, ionic bonds are formed by sharing of electrons that create electrical differences between a cation and an anion. And hopefully you said false, because they don't share. They either give or take. Sharing is something completely different. which is a covalent bond. N is the next type of bond we're going to look at. So covalent bonds work by sharing two electrons within valence shells or valence orbitals. It allows each atom to fill its valence shell at least part of the time. And these happen between two nonmetals. So you can see here, this guy needs 4 more electrons. So instead of giving them, he just shares them between these guys, right? And then you have 2 oxygens here. As you can see, they have 2 pairs of electrons that are bonded together in perfect harmony, but then they share these 2. And it's easy to tell if something's going to be a covalent bond by if they are 2 nonmetals. Now, the easiest way to figure out how they're going to bond is by using what are called Lewis dot structures too. And a Lewis dot structure can kind of tell you in regards to how many bonds it can make with something else. So the Lewis dot structure for carbon Lewis dot structures use the basic shorthand here. And then it just uses how many valence electrons we have. So for carbon, we have 4 valence. And this is just saying, okay, each corner here is an orbital. And just to let you know, you want to fill as many orbitals as you can first and then pair them. It's like, say for instance, if you have a subdivision and you have 4 houses and you have 4 people, and in each house can hold 2 people. Which sounds more logical to you guys? If you want all 4 houses to be working properly, would you fill your 2 homes to the brim and just have 2 homes where people are looking after? Or would you put 1 person in each home to make sure all your homes are looked after? And for us, if we want to make sure we have 4 rental properties, we've hired 4 people, we're not going to put 2 people in 1 house because then we're going to have nobody in our other 2 homes, right? So you're going to hire 4 people and you're going to put 1 person in each home. And because they're occupying each home, that is more stable for their homes, and the homes are going to be able to be well looked at versus putting 2 people in 1 home than having 2 of them being ignored. So that's basically when we're talking about orbitals, what's most important. So when we're doing this, the Lewis dot structures are as seen above. So we have 4 electrons in carbon, which means we need 4 more. So you take your shorthand form of carbon, whatever the symbol is, and then each corner is going to represent an orbital. So we have an orbital here, and so we're going to write an electron here, here, and here. So that tells us we have 4 other 4 other electrons we need. And so if you look, we have hydrogens here. He has 1. He has 1. He has 1. And he has 1. So they're going to share them between each other. And so that's how you write them out. And then that's how they demonstrate sharing between the different orbitals. And so this is methane. And this is because if you look, let me get out of here and go back here, and you can very easily see carbon, hydrogen, right? So that's going to be a covalent bond. H2O, right? Water, oxygen, hydrogen, going to be a covalent bond. Methane, no, they have oxygen there in a second. Oxygen, oxygen, two nonmetals, right? So that's how you can tell what's going to be a covalent bond. Now, if we do the Lewis dot structure here, you'll see that there are 6 electrons here. So you go and you go 1, 2, 3, 4, and then you have a couple of them that'll be paired. So these are already stable, right? There's 2 of them here. So this tells you there's 2 bonds that can be formed. So this is covalent bonds in general. Now, there are a difference between, there's 2 types of covalent bonds. There's what's considered nonpolar, which means they're shared equally. And polar, which means they're unequal. So one side is going to be more negative than the next. And when you're looking at molecules, you can look at bonds, and then you can look at molecules themselves. And a whole molecule is polar because one side will be slightly more positive than the next. So let's look at this. For instance, water here, okay? Let's look at each bond type that we have. Well, if you remember, we have 1, 2, 3, 4, and I always do this, 5, 6, right? So on here, actually, let's go 5, 6. So on here, we can actually make 2 more, right? Bonds, and we know hydrogen has 1. So we have these 2. Now let's look at how many electrons that we actually have going on here. These, you're looking at the 2, right? In here, you're looking at 2, 4, 6, 8, right? That are going on in the valence up here. Now, which one has more electrons? The oxygen. So even though this is shared, the electrons, there's going to be more electrons on oxygen, and even the hydrogen electrons are going to hang out on oxygen a little bit more. I like to think this kind of in the idea that if you live next door to your best friend, you guys share a patio, you have each separate apartments. And this is your apartment, the hydrogen. And you have a bed, and you have your little TV and couch, and that's about it, right? And your friend next door has any and almost every kind of gaming system you can, surround sound, has like HBO, all kinds of great stuff, has all the food, pool table, everything you possibly can imagine. Well, you're going to be hanging out at your friend's house all the time because they have all the really cool stuff. But you're still going to go back home because A, your bathroom probably is cleaner because everybody's hanging out at your friend's house, and you can get some quiet in your own bed. So this is the idea that the electrons like to hang out there more because there's more electrons there. It's more electronegative. Think electronegative as in electrons and being more negative on one side, but you're still going to hang out at the hydrogens. So this is going to make, when we look at this, guys, the hydrogens are going to become slightly more positive because the electrons are hanging out there less, right? And this side is going to become slightly more negative. And so if you look, this side of the molecule is slightly positive. This side is slightly negative, and that's what ends up becoming a polar molecule because this is slightly more negative than this side. So that's what polar molecules are. Non-polar molecules are going to be, there's not this charge differential. So something like this, methane, or fatty molecules have the same thing happening. There's slightly more electronegativity happening on carbon. So everything goes towards the center. But do you see how there's no positive on one side versus the other? So this is a nonpolar. Polar and nonpolar don't like each other. Oil is nonpolar. Water is polar. Oil and water don't mix. So that gives you kind of an idea on the different types of polarity. And so this is just kind of showing you symmetry in the sense of what I was just talking about. This is methane. You can see that all the way around it is positive on the inside, positive on the outside. So there's no polarity. Now, if you add a negative part on one side, then this becomes slightly positive, this becomes slightly negative, and now it's a polar molecule. But on this point, do you see how you've replaced every single side with a negative one? So again, this is nonpolar. So it depends on where the molecules are in terms of your, it depends on where the atoms are in terms of your molecule and as to whether it is polar or nonpolar. So let's look at this and let's determine really quick for you which molecules are nonpolar. Now I can give you a hint here. If it has something like oxygen on one end or nitrogen on one end, then it is considered nonpolar. One moment, please. Do you have oxygen or nitrogen here? No. So this is nonpolar. How about here? Oxygen on one side, right? And we just talked about this. So this is polar. How about this guy? You have oxygen here, so it's going to be polar. And this one, it has a nitrogen, so it's going to be polar. So that's kind of a hint. So if you have any of these on one end of a molecule, it can give you an idea that it is polar. So the only thing that is nonpolar here is A. And so when we're looking at here, you can kind of get an idea. We've already basically looked at these two guys, right? So ionic bonds are transferring, give or take. It's going to make them positive or negative, and that's what's going to keep them together. Polar molecules are a sharing, but it's unequal. Remember, one side hangs out, the electrons hang out on one side more than the other. So an example of this is water. And the nonpolar is an equal sharing. There's not a polar share, like one side getting a more than the other. And this is an example of carbon dioxide, or even something common that we talk about, especially when we get to lipids, things like methane. The last part is the hydrogen bond. And I'm going to pause here to let you guys think for a minute, and we will get to this in one moment.